Welcome to your chapter on 3D shapes. Get ready to move and learn. We will explore cones and spheres. Let's begin our review.
Everything around us occupies space in a specific way. To make sense of the physical world, we categorize objects by how they exist in space, using dimensions. This diagram shows the simplest form of measurement, a one-dimensional shape. It has exactly one metric, which is length. It represents distance from one point to another, with no thickness at all. When we take that line and stretch it out in a second direction, we add width. This creates a two-dimensional shape, existing entirely on a flat plane. As the text in this section points out, two-dimensional shapes occupy space strictly on a flat surface. They have a measurable area, but they hold zero volume. While two dimensions are perfect for measuring fields or drawing blueprints, they hit a wall when we try to describe solid objects. To map the physical world, we have to move into the third dimension. By pulling that flat rectangle backward, adding height or depth to our length and width, we generate a three-dimensional object. Now it takes up actual physical space. Looking at this exercise, we can sort everyday items, separating flat surfaces from solid forms. Notice the precise wording. A carom board is solid, but its surface is strictly two-dimensional. In contrast, the spinning top next to it is categorized entirely as a three-dimensional object. Three-dimensional objects are defined by the volume they hold, while two-dimensional shapes often serve as the flat boundaries that enclose those objects. To accurately measure and build these objects, we need a precise vocabulary to describe their structural parts. This two-dimensional rectangle breaks it down. Straight perimeter lines are sides, and corners are vertices. Moving to the three-dimensional cuboid, the flat surfaces are faces. Lines where faces meet are edges. Crucially, a side bounds a flat shape, while an edge intersects two faces. Mastering these exact terms gives us a systematic way to describe the skeleton of any physical structure or theoretical model. Returning strictly to two-dimensional space, we classify closed figures with straight sides as polygons, naming them based on the total number of sides they possess. This table lays out the mathematical progression. A polygon with 3 sides and 3 vertices is a triangle. Add a 4th side and you get a quadrilateral. 5 sides make a pentagon, and 6 make a hexagon. As you continue adding sides, the internal geometry grows increasingly intricate. Yet, no matter how many sides a polygon has, it remains entirely flat, permanently locked in 2 dimensions. We can see how this geometry translates to real life through practical application. This illustration shows a student filling an empty matchbox with wet soil. When the soil sets and the box is removed, the hollow 2-dimensional constraints of the box produce a solid 3-dimensional brick. Let's test this categorization in real time. Try identifying whether these common items act as 2D surfaces or 3D objects. A single sheet of paper, a soccer ball, a shadow cast by a tree on the ground. Differentiating between a surface and a solid allows architects and engineers to calculate volume, determine material costs, and physically manipulate the environment. Geometry provides a universal language to map the dimensions of reality. It gives us the tools to scale up from the simplest line drawing to the construction of massive real-world structures.